Okay, in this video, we are going to focus on two centers of the triangle. I know the last video we talked about all of them, but here we're going to kind of narrow it down a little bit. Before we get into that, though, just to talk about that vocab word concurrency again. When three or more lines intersect at one point, we say the lines are concurrent. And the point where the lines intersect is called the point of concurrency. And based on whatever feature of the triangle we're focusing on, that point of concurrency will be one of those specific centers of the triangle. Okay, so for today, we're focusing on perpendicular bisectors and angle bisectors, which we did start our chapter off with. But now specifically talking about what happens when they're in the triangle as opposed to just random perpendicular bisectors or angle bisectors. Okay, so for perpendicular bisectors, remember, they can start at one of the vertexes of the triangle, but it does not have to. So the shape that they gave right here, they did not actually put the perpendicular bisectors in. So you don't have to do this. I'm just kind of going to throw it in here. I'm going to eyeball it. So I'd say like that's a perpendicular bisector. Probably right here is a perpendicular bisector. And then this one would be like right here. Okay. So that's where they're getting this point of concurrency from. Okay. So those perpendicular bisectors. Okay. But what happens, and we mentioned this the other day, once you have that center, that point of concurrency where they all intersect, we said the distance from that center to all the vertexes of the triangle, all vertices of the triangle, sorry, are all congruent. And why this is kind of cool, we kind of have to talk about some circle vocab, which I know we haven't done circles yet. Okay, but when you have circles, a circle goes around a shape, okay, where the circle is laying on all the corners of that shape. In this case, the shape is our triangle. Okay, we call that circumscribed. So it says the circle that contains all three vertices of a triangle is the circumscribed circle of the triangle. Okay, so this circle here, okay, is going around, hits that corner, that corner, that corner. Okay. And what happens is this is a radius, and this is a radius, and this is a radius. And all of the radii in a circle are going to be equal to each other. So that's why that happens. And that is also why we call this the circumcenter, because it is circumscribed around the entire triangle. Okay. So now let's look at what some questions can ask us here. We have the perpendicular bisectors of triangle ABC are PT, QT, and RT. So in this one, we do have the perpendicular bisectors. We also have that distance, okay, from that circumcenter to the vertices. So we have all these segments here, okay, and we are going to find each value. So first off is AT. Now AT is this one right here, which is the distance from the circumcenter to corner A. We have learned that that is going to be equal to all the other distances from the circumcenter to the respective corners. So in this case, while we don't know AT from the diagram, we can see that CT is 6, which means that AT is also going to be 6. Okay, because that and that and that are equal to each other. The next one is RC. Okay, here we are actually using the fact that this is a perpendicular bisector, which means RT bisected side AC, and we can see that AR is 5. That must mean that RC is also 5. Okay, and then the last one, RT. RT is right here. Okay. Here we do see that PT is 2, but we cannot say that the perpendicular bisectors themselves are congruent to each other. They are not. Okay. But what is also happening here is because they are perpendicular bisectors, they form right angles. And this is actually going to be a Pythagorean theorem question. So we know in this particular one that CT was 6. RC, we just figured out that was 5. we're trying to figure out RT. So we'll say something like a squared plus 5 is the other leg. So 5 squared equals the hypotenuse squared, which is 6 squared. So we have a squared plus 25 equals 36. We'd subtract 25 from both sides. So a squared equals 11. And then square root both sides. Normally we would say plus or minus, but it's geometry, so a side can only be positive. So square root of 11. So RT is going to be square root of 11. Okay, so a couple things going on here. Okay, in part letter B, we had the fact that these were perpendicular bisectors. So if you looked at the big sides of this triangle, they had to be broken up into equal pieces. We had the fact that the circumcenter creates these pieces going from the circumcenter to the angles of the triangle that are all congruent to each other. That's the feature of the circumcenter. That's what we needed for letter A in this. And then we also had the fact that the perpendicular aspect of things created right triangles going on here. So we had to use the Pythagorean theorem to find missing pieces. So it's not super hard, but you definitely have to look at your diagram, look at what's going on, okay, and fill in missing pieces where you can, and then see what relationships are going on amongst those pieces. Okay. Before we move on to the other part, the circumcenter can be in several places based on what type of triangle we have. So if we have an acute triangle, the circumcenter will be on the inside, the interior. If it's an obtuse triangle, it's actually going to be outside of the triangle, which is kind of interesting because you think a center of a triangle probably wouldn't be outside, but it is. And then the last one, if it's a right triangle, it's actually going to lie on one of the sides of the triangle. Okay. And our other aspect of things are angle bisectors. Okay, so these are obviously coming from the angle because it's bisecting the angle. Our other circle vocab word that's important here is that if a circle intersects each side of a triangle at exactly one point and it lies within the shape, okay, that's called inscribed. Okay, so once again, we had our angle bisectors here. You don't have to draw these in, but like here's an angle bisector. Here's an angle bisector. Here's an angle bisector. So they met right there. That's where they got that center from. Okay. We said when we did this the other day that the distance from that center to all the sides is all going to be the same in this case. Okay. And once again, when a circle can be put inside of a shape, we call it inscribed, which is why this center is called the incenter. Okay. And once again, the distance from the incenter to all the sides of the triangle, they are all radii of that tiny circle, and which is why they are all equal to each other. Okay, so we have a shape down here. It says two of the angle bisectors of triangle ABC are AP and BP. Okay, we don't have PC there, but I don't think we need it in this diagram in this case. So the first thing is that we want to find PK. So P is the incenter, and we said that JP, PL, and PK all have to be equal. Okay, they are all the distance from the incenter to the sides. And we know those are all the distance from the incenter to the sides because we see all these little squares here showing that that segment is perpendicular to that side of the triangle. Okay, remember, the shortest distance is perpendicular. Okay, so we see JP is 5, and that must mean PK is also going to be 5. Okay, and now we have to do the perimeter of triangle APL. So that's this triangle down here, APL. Okay. We see that this is 13. Okay, so AP is 13. That's what it's talking about. what happens here, okay, um, it actually forms some congruent triangles. So we know that, here, I'm going to mark this up a little. We don't have to do this every single time, but I'm just showing you why this works. So we knew that if this is an angle bisector, that this and this are congruent. We know AP is congruent to itself. And because these are right triangles over here, okay, we can prove that those two things are congruent by angle, angle, side. Okay, and the reason that's important is because now we can use this idea, if they're congruent by angle, angle, side. Okay, this piece that is 12 right here would match with this piece right here. So this is also going to be 12. Okay, so in this in-center question, okay, the pieces on the that are kind of across from each other next to those angle bisectors, those are going to be equal to each other. So like LC and CK will be equal, and BK and JB will also be equal. Okay, so you don't have to go proving it, but we do know that because this is 12, this will also be 12. Okay, and then that leaves us with PL. Hopefully you're realizing that that is a right angle. So once again, this is a Pythagorean theorem question, but it happens to be a nice Pythagorean theorem. If you go back way to the beginning of school where we talked about our Pythagorean triples, and I said you don't need to know them. Okay, I'm not going to test you on them, but they certainly come in helpful at times. This is one of those times because this is a 5, 12, 13 triangle. Actually, sorry. You actually didn't need Pythagorean theorem there. I'm being silly. Okay, well, you could have used Pythagorean theorem, but since we knew JP was 5, PL is also going to be 5. So either by Pythagorean theorem or the fact that we already knew one of those other distances, okay, it is a 5, 12, 13. And then we can find the perimeter of that triangle. 5 plus 12 plus 13 is going to be 30. Okay, and the in-center is always going to be inside our triangle in this case because we said that that circle is going to be inside of the triangle. Okay, so in this case, once again, when you know the in-center, all those distances from the in-center to the sides, those are all equal. The pieces that are, I say across from each other, I know it's not really across, but here and here, we said like those are going to be equal to each other. So you could possibly need Pythagorean theorem in certain cases. We didn't have to here, even though I thought for a second that we did. Okay, so we are going to now practice these. Once again, just take it slow, fill in whatever information you have, and use those features to help you figure out the missing pieces.